Good morning, student. Today we are going to see condition for Jahn-Taylor distortion. First condition is no distortion condition. If both T2G and EG orbital are filled symmetrically, the word symmetrically stands for if both the set of orbitals are empty, if they are half filled or they are full filled, there is no gain of extra stability by undergoing distortion. Hence, in that case, there will be no distortion. Such a condition arises when d orbitals have following configuration. So, we are going to see in what electronic configuration basically there is no distortion. So, if your d orbital have 0 electron, then electronic configuration can be written as T2G0 E0. In this case, there is no distortion takes place. In D5, if your d orbital have 5 electron, then electronic configuration of splitted orbitals can be written as T2G3 EG2. So in this case also there is no distortion. In D8 configuration, if a configuration is like T2G6 EG2, then there is also a no distortion, because if we see here, the overall capacity of T2G set of orbital is 6, while EG set is here 2 orbital contain 1 electron. So they are basically, this set of orbital is completely fulfilled and this set of orbital is half filled. So in this case also there is a no distortion. In the D3 configuration, all the electron goes into T2G set. Each T2G set contain 3 orbitals, so each orbital have 1 electron. Because of that, this set is half filled, and EG don't have any electron, so it is empty. That's why it is also no distortion condition. In D6 orbital, if d orbital have 6 electron and that electron is placed in this fashion, that is T2G6 and EG0. So in this case, T2G set of orbital have fulfilled configuration while EG set is empty. So in this case also there is a no distortion takes place. In D10 electronic configuration, your T2G set contains 6 electron while EG set contain 4 electron. In this case, your T2G set have fulfilled electronic configuration and EG set also have fulfilled electronic configuration. That's why this set is also does not show distortion. Now what second condition is slight distortion condition. Slight distortion in the geometry is observed when your T2G orbital are filled unsymmetrically. That is for T2G1, T2G2, T2G4 and T2G6. If we see here, each this set T2G in each electronic configuration, they are unsymmetrically filled. This is because these orbitals are not directly pointed towards the ligand. Because of that, there is slight distortion in the geometry of your complex. Now what is the strong distortion condition? Strong distortion or strong deviation from regular geometry is observed when EG orbital are unsymmetrically filled. As these orbitals are pointing towards the ligand, such a configuration are EG1 and EG3. If your EG orbital have 1 electron or it have a 3 electron, then this electronic configuration is considered as unsymmetrical electronic configuration, and because of that there is a strong distortion in the geometry is observed. Now we are going to see absorption spectra of the what is the absorption spectra and what is the concept behind the absorption spectra. Now according to CFT, the d orbital of metal split up in the presence of ligand in 2 or more level, just like T2G and EG. The energy gap between these energy level generally correspond to visible region of the spectrum. That is, the energy gap between T2G and EG orbital is generally corresponding to the visible region of the spectrum. It is most important thing. When light falls on the complex, electron gets excited from lower d orbital to higher d orbital. Light of specific wavelength is absorbed and the complex look color. It is also very much important thing. We discussed this thing in detail in next topic. So just pick up this point. Different complexes show different color because due to the difference in metal, ligands or geometry, the extent of crystal field splitting different. So the energy required for DD transition is also different, and hence different complexes have different color. In case of octahedral complexes, the electronic transition takes place from lower energy, that is T2G, to higher energy, that is EG orbital, while in case of tetrahedral complexes, the transition takes place from lower energy E orbital to higher energy T2 orbital. The color observed is complementary to that absorbed wavelength. This is the most important thing. Now just see here, wavelength of absorption, color absorbed and color observed. Now the region 400 to 435 nanometer, in this region violet color is absorbed. While violet color is absorbed, observers see yellowish green color. For example, if a violet color from ordinary light is absorbed, the resultant color seen by the observer is yellowish green. If 435 to 480 nanometer, in this wavelength blue color is absorbed, but the complementary color, the color seen by the observer, is yellow. When we say this complex looks yellow, basically that complex absorb the blue radiation which is come in the region 435 to 480 nanometer. 480 to 490 nanometer correspond to greenish blue color absorbed, and the complementary color which is seen by the observer, it is orange. 490 to 500 nanometer, in this region basically bluish green light is absorbed and color is seen by observer is red. 500 to 560 nanometer, it is the region of green light. When green light is absorbed, the color seen by the observer is purple. When 560 to 580 nanometer, this region is basically of yellowish green light. This light when absorbed, the color is seen by the observer is violet. 580 to 595 nanometer, in this region yellow light is absorbed and the color seen by observer is blue. 595 to 610 nanometer, it is the wavelength corresponding to orange light. When this orange light is absorbed, greenish blue color is seen by the observer. When 610 to 750 nanometer color is absorbed, that is red color is absorbed. This is the wavelength of your basically red color. When this red color is absorbed by the complex is seen by the observer is bluish green. So complementary color is seen by the observer, not the absorbed color. Now selection rule for the electronic spectra, it is most of the important thing. Student, please make note of that. There are two rules. First rule is known as Laporte selection rule. Second rule is known as spin selection rule. So first we are going to see what is Laporte selection rule. According to Laporte selection rule, electronic transition takes place if the parity of molecular orbital is changed. Now what is the meaning of parity of orbital is changed? It simply means that Gerard to ungerard or Gerard to ungerard or ungerard to Gerard transitions are allowed, while Gerard to Gerard, ungerard to ungerard orbital transitions are not allowed. Second rule is known as spin selection rule. According to this rule, electronic transition is allowed between two states having same multiplicity. It is important, having same multiplicity. So singlet to singlet or triplet to triplet transitions are allowed, but triplet to singlet or singlet to triplet transitions are not allowed. In other words, we can say that the spin of electron should remain same after excitation. Now we are going to see absorption spectra of hexaco-titanium 3 plus. So electronic configuration of titanium is Ar3d2 4s2. In this complex, titanium is basically 3 plus oxidation state. So titanium 3 plus can be written as Ar3d1. So this is the 5d orbital of titanium 3 plus. In this orbital, basically there is one electron. In presence of ligand, these 5d orbitals get increase in energy, but they are in a degenerated state. When ligand come close to this metal, that is titanium, this set of orbital is basically split up into two sets, T2G set and EG set. Why it show octahedral splitting? Because it have 6 ligands. So this electron is basically goes to the lower energy state, that is this electron basically comes into T2G set of orbital. So when this complex is put under the light is absorbed by this electron, and this electron can shift into EG orbital. So hexaco-titanium 3 plus is basically a purple color complex. Now it is important, it is the purple color complex. It simply means that the color absorbed by this complex. So just see here, if it is a purple color complex, the color absorbed by the complex is green. So it is come nearly at 500 to 560 nanometer region. So this is the absorption spectrum of hexaco-titanium 3 plus complex. So in this complex, just see that we see here a hum nearly at 500 nanometer. We see here a hum, that is absorption maxima here. Now students should note that this is not a single light, it is the broadband signal, broadband. Beside that, it is not symmetric signal, it is unsymmetric signal. This signal is unsymmetric in nature. So we are now going to see why this signal is unsymmetric in nature, why it is not comes as a single line, why this is comes as a broadband. So the absorption band appears at about 500 nanometer. It is nearly 2000 centimeter inverse. This wavelength corresponds to energy of 240 kilojoule per mole inverse. This value is comparable to the separation of T2G to EG orbital. It simply means that nearly 240 kilojoule per mole value is required, or it is used for the separation of your T2G to EG orbital. It is clearly shown that the band is obtained by the transition of d electron from T2G to EG. Since there is only one d electron, a single band is obtained. This type of transition is called DD transition or ligand field transition. So we see that T2G set of orbital contain only one electron. So by absorption of light, this electron can be shifted or goes to higher energy level, that is EG, and there is only one possibility of this, and that's why there is a single band. Now it can be seen that intensity of band is very low. Intensity of this band is very low, with molar absorptivity epsilon having value near about 5. In many other cases this value is much higher, that is 10 raised to the power 4. The reason for this is that the transition from T2G to EG in octahedral complexes is forbidden by Laporte rule. Now what is the Laporte rule? Laporte rule says that according to Laporte rule, Gerard to ungerard and ungerard to Gerard transition are allowed, but Gerard to Gerard and ungerard to ungerard transition are not allowed. Basically, in this case, dd transition takes place, that is electron from your this d orbital goes to the electron goes in Eg set of orbital which also contain d orbital, and because of these d orbitals basically are having same symmetry, because of that these transition are forbidden by Laporte rule. According to this rule, the transition of electron from one centrosymmetric set of orbital to the other centrosymmetric set of orbital is forbidden, as it can be seen that both T2g as well as Eg set have center of symmetry. Such transition should not take place. In that case, there should be a zero intensity. However, a small intensity indicates that the orbitals are not perfectly centrosymmetric. This is very much important. This may be due to the partial mixing of orbital, that is Eg set of orbital are partially mixed up and ligands. This may be due to the partial mixing of orbital of Eg set of metal and ligand. If such a mixing takes place, then the first postulate of CFT, that bonds between metal and ligand is purely electrostatic, does not hold good. This is one of the limitation of CFT. In a next class, we are going to see with of some more point about absorption spectra of your titanium hexa echo titanium 3+ complex. Thank you very much.